Good day, everyone. Thank you for sitting in and for joining in today's presentation. My name is Dayo Olupona, and I'll be sharing my PhD progress with us all. I'm a PhD student with the University of the Witwatersrand under the School of Mining Engineering. So in today's presentation, I'll be sharing on the topic Towards Uninterrupted Mining Operation, Predictive Maintenance Approach with Artificial Intelligence. I'll be touching on all the phases that will be covered in this project. Firstly, with the background, where I would give a bird-eye view of the presentation and the project so that we can have a view and a background of where we are coming from and where we are going. Secondly, I would share on the current stage of the project, what has been done, and thereafter I would briefly speak about what is supposed to be done for the project to be complete. So with the goal of improving equipment performance and efficiency, this project aims to firstly identify, secondly design, and thirdly implement a pilot predictive maintenance AI solution for equipment and machinery that are used in an open cast operation. So basically, the output would be to design a model that is useful in predicting the failure of machines used in an open cast operation. However, the choice of open cast operation has been changed to underground, as we can see on this slide. And the reasons for this will be discussed later in the presentation. As I currently speak, the identification phase of the project has been completed. And in this phase, we sought to identify a number of factors and variables that would influence the success of this project. The first being identification of the companies whose mine we would use for the study. The South African Coal Processing Society was supposed to assist with identifying some of the mines, but we couldn't get a favorable response. And through our other sponsors, we were able to identify 3 mines, as we can see on the screen: Company A, Company B, and Company C, with their mines volunteering data. Company A has been the most responsive and has volunteered the first phase of data that will be collected to give us, and would use that to design some of the things that are going to be used for this project. We can see in the later part of this presentation how some of the data has been used. So based on that data, we made a number of consultations, which included professionals in the field, academia, and also the equipment manufacturer, to identify the machine that would most be impactful to conduct this research on, that is an underground equipment. And out of all of the list considered, the choice was the continuous miner. And for this continuous miner, 2 major data types will be collected. As we can see here, the maintenance data and the machine data and sensor data will be collected. So the maintenance data was collected from Company A's mine, one of Company A's mine, and the machine data or sensor data is being collected from Komatsu, which is the original equipment maker or manufacturer for the continuous miner used in that particular mine. As mentioned in the last slide, 2 broad set of data were collected, and they are the delay data and the machine sensor data. So the delay data is a type of maintenance data, and it's simply a record of all the faults and the damages and the failures that has been recorded in the logs of the maintenance team. So it was provided to us by the maintenance team of Company A's mine, And secondly, we have the machine and sensor data. This was provided by the original equipment manufacturer, and it's simply a record of all the sensors pertaining to the machine, and it takes record of all the activities that the machine is partaking in at a particular point in time. Close to 400 sensor tags were on this continuous miner that we are currently studying, and we look forward to using that productively. So a combination of these two data types are what is needed for us to completely design the model that we are focusing on for this study. Here is a breakdown of the phases that needs to be completed for this project to be successfully completed. So we have about 5 of the phases. 3 are blurred out, and the 2 are going to be discussed in these slides. As we can see that there's been a slight change in the schedule of the project because of some of the reasons discussed earlier, the identifying of the mines and collection of data. But nonetheless, the first phase has to do with the preliminary site and equipment or plant review, and identifying the operational use case of artificial intelligence and machine learning, and that was carried out sometimes 3 months ago. Then we were able to make the recommendations that we made and discussed in the earlier part of the slides. So the second phase is identifying the 3 most suitable and adaptable use cases, and that is where we are currently at, and the next couple of slides will discuss how that is being achieved. As previously mentioned, the first phase of data collection has been completed, and in the next 3 slides I'll be sharing what has been done in the area of data defining or data definition. So the data definition process is simply a preliminary data analysis that is carried out on the collected data, and one of the benefits is that it helps us to focus our use cases. Also, it helps us to see how best to integrate the 2 data type that was mentioned earlier for the best project output. So a literature review, an extensive literature review was carried out, and the first realization from the review and experts combined with experts consultation is that it is difficult to carry out machine level diagnosis and prognosis with artificial intelligence and machine learning, especially within the typical mining and mineral processing environment. One of the reasons, amongst many others, is that the machines used within our industry is complex, and in addition to the complexity, they have several systems, they have multi-components, and in most cases these components are dependent on each other. So it is always preferable, based on these studies, to identify selected essential and critical components that can be focused or can be the focus of the study. So hence the machine is broken down into subsystems and systems and components, like we can see on this slide. So rather than focusing on the machine level, it is advisable to come down to the systems or the subsystem or the components level, and this is where the most value can be achieved. So in essence, for a project like this to make the most impact, multiple subsystem level and component level projects like mine, or like the one I'm presenting, needs to be done and needs to be funded in order for us to achieve this overall machine level predictive maintenance that we all strive for. So on the screen is the fault frequency distribution of the continuous miners data collected, log data collected. And it shows the subsystem and the component level and the number of faults and failures that were identified from the log data or from the delay data sheet that was previously discussed. So a quick scan of these fault tags helped us identify about 3,000 failures within the time frame that we looked at, and for the particular model of the continuous miner that we focused on. So as we can see, this major speaks to the system and the minor speaks to the subsystem and component level. And we've highlighted three portions for us to look at, and we can see that within this instrument and control system, the protection devices and the alarms had the highest number of failures, and it was close to 800. Similarly, we can look at the quarter system of the continuous miner. The water system there had a number of issues, and also of note is, systems and components like motor electric, which had 88 failures. We can also look at the hydraulic systems where we see the pumps have 36. We see the pipes and fitting having over 100 failures. So like I mentioned, the focus would be on the subsystems and the component level, and these three highlighted portions will be expanded in our next slide, and it will give us a good sample size and help us see how we can use it to further improve the integration into sensor data to make sense of what it is that we are doing. So to reiterate the importance of this analysis, our goal is to use this log data or this preliminary analysis to identify the subsystems and components that we're going to focus on for this particular study. And the second is to see how to best combine it with the machine data or the sensor data for us to get the model that we are looking at. So we can see that the focus area are those highlighted from the previous slide: the quarter system, the instrument and control system, and the hydraulic system. And in each of those systems, we can see that the frequency of some are quite high and the frequency of some others are very low. So for instance, the telephone under the instrument and control component is very, very low. The gearbox is quite low. The pump is also average. We can also see the chassis and frames that are very, very low. We can see that of the protection devices, as mentioned in the previous slide, as very high, and the water system too as very high. So making a decision, it has a lot of variables that has to be put in place and also be weighed against each other before decisions of the particular components can be. So here is further analysis of the subsystem and the components level of the continuous miner, and here we are looking at the highest and the least breakdown duration in hours. So just like the previous slides, we are looking at the three focus systems: the quarter systems, the instrument and control systems, and the hydraulic systems. So even though we saw a very high number of frequency in the protective and devices alarm, here we can see that the highest number of breakdown duration for the components in this system is 19 hours. But as compared to water systems, we had breakdown of close to a day of 24 hours in water system. We had it once in a while. We can also see gearbox, even though it was very low in the previous slide, but we can see here that there was probably a number of breakdown that was close to 19 hours. Similarly, we can look at the pump. It has about 15 hours of breakdown. So to help us dissect it further, we can see that frequency is important, but as much as frequency is important, the duration of the breakdown help us know what equipment or what component to focus on, because we can avoid similar breakdowns happening in the future. But if you look at the average breakdown and the average hours of breakdown, which is in the mean, which is the orange color, we can also see that even though protection was very high, that means the mean breakdown is around 1 hour, close to 2 hours, of which we have higher ones in the pumps. The pumps had about 4 hours averagely. So if this one fails, there's a chance that it's going to be about 4 hours. Similarly, we can look at the gearbox. If the gearbox fails, it's roughly going to be about 3 to 4 hours. And we can also look at the the cylinder 2 gives us an overview of about 2 hours averagely, and the highest being about 10 hours of breakdown. And we should not forget that every breakdown within the industry costs money, so it is preferable to minimize those breakdown in one way or the other. And that's the essence of this study, to see how we can design a system that can tell us that this machine is about to break down in the next couple of days, or this component is about to break down in the next couple of days, and we schedule maintenance appropriately. So in this study, we can just look at three things that, or three components that we can rather focus our study on. So based on consultation and speaking with the experts, particularly the OEM manufacturers, looking at this, we saw motor electric as one of the components that we might focus on. We can also see that of gearbox, and we can also see that of the water system. The water systems. The pumps also is something to consider, because averagely is 4 hours. Averagely that of motor electric is about three hours plus, and the same thing for the gearbox. But nonetheless, in addition to all of this, we also are looking at how we have sensor data relating to all of these components. So all of these components will be combined with their sensor data to get the most output from it. So if a telephone doesn't have a sensor data, there's no essence in trying to focus in that area. So like I said, all of these variables will be very important in designing that model. One other important point is, while discussing with the expert on the field, they also pointed our attention to beyond the average of the protection devices. So for instance, this could also be as a result of methane emission. Once the sensor detects that there's a methane emission, it trips the machine. So that could be one of the reasons why we had so much frequency, but the average was very minimal. The average was about 1 hour. So this in itself, it's not a major fault, it's a warning signal that can be attended to in time. So it can be eliminated from the choices of components to focus on for this particular study. So in essence, there are a few more analyses that will be done, or preliminary analysis or data definition that will be done to eliminate the non-essential components and focus on the critical and the essential components. And that's one of the things we'll be working on continually in this research. So in addition to the analysis that has been done previously, here are some other milestones that has been achieved with this PhD study. So the first is that we've been able to collect data that we discussed. We've also built relationship with the industry, which is critical to the success of this report or this research. The other is that we were able to present a conference paper, peer-reviewed, in Turkey, and this is a topic, predictive maintenance, a viable maintenance option for machines, equipment, plant in mining and mineral resources. And also, secondly, we are working on a scholarly journal article that reviewed over 200 articles and should be published very soon. It is under internal review, and we are looking to publish the outcome of that that study. So that's some of the milestones that we have had with this project. So having made significant progress with the two options that was discussed earlier, here are three other things that will be done for this project to be complete. The first, number three, is the pilot predictive AI design, training and testing. And for us to achieve that, we need to define the data as described earlier, figure out where to focus on, combine that with the sensor data, and once that has been completed, then we can completely design the model, train the model, and test it for the field. And once that has been completed in December 2023, we are going to look at how we can operationally deploy it to test and refine it for the optimal use, just to make sure that we get the best use of the model. And the feedback we get based on this use is going to be what we feed back into the model to refine it for operational use and deployment for the minds that are in this community. And the last phase is the operational result analysis and final report, where we present all of our findings and what we achieved from the testing, from the designing, and from the training, and literally share with the teams at South African Coal Processing Society and also Coal Tech. And on that note, I would like to thank our sponsors in the persons or in the associations of South African Coal Processing Society and the Coal Tech Research Association. Thank you very much. And I would also like to acknowledge my supervisors, the presence of Professor Samson Bada, Professor Bekil Genj, and Professor Toge Selik for the immense contribution into this research. Thank you.